Okay, we're going to get started with the notes for Unit 3. So if you guys remember Unit 2, we dealt with kinematics, so why stuff or how stuff moves. Unit 3, we're going to deal with a little bit more why stuff moves. So we're going to start with Newton's second law. There are 3 laws. We're going to go a little bit out of order. We're going to start with Newton's second law. To really get into the law, first we have to talk about a couple quantities. The first is the amount of material in an object. So that's an object's mass. That's important. Should be reviewed from earlier science classes. Remember, mass is really, it's not about how big something is, it's how much stuff is in it. Mass has the symbol m. It's a scalar, meaning it does not have a direction. And it has the unit of kilograms. So if we wanted to represent it, like on this box, this little m stands for the mass. The other quantity that's important is force. So this is a new idea. You've probably heard it, but it has a very specific physics meaning. So force has the symbol F. That's going to be what causes an object to accelerate. So again, without forces, there is really no acceleration. There's no change in velocity. And that would be symbolized with an F, like on this box. This F would be providing the force. So force, again, it does cause an acceleration. Sometimes it's helpful to think about it a little bit more conceptually. It's really just a push or pull, and that push or pull is going to cause the acceleration. Force is a vector, so it does have a direction. Like in this box, the force is to the right. So again, it does have a direction and a size. It has a standard metric unit of newtons. So newtons abbreviated with an N. Also, you might see this unit, a kilogram times meter per second squared. That's also another unit for Newton. We're going to deal less with that, more with the Newton. So more with the N will be the standard unit. And then the last kind of new idea before we can talk about the law, which is down here, before we can talk about this, is going to be net force. So the net force is the sum of all the forces added to up. And you're going to see an example of exactly what this is a little bit later, but net force, it's the sum of all the forces. It has the symbol sigma F, so it's like a squiggle, and then F, that squiggle just means net, so it means to total up all of the forces. And again, we'll see an example a little bit later, but that's the idea of net force. So Newton's second law really calls on those concepts, and Newton's second law, what it does is it relates acceleration, so again, change in velocity with time, to an object and its mass, as well as the net force on that object. So it really gives us a nice mathematical basis to look at how something's accelerating. So this is the equation right here. So acceleration A, should be familiar, is equal to the net force over the mass. So again, if the net force gets bigger, you'll have more acceleration. If the mass gets bigger, you're actually going to have less acceleration. Sometimes it's written like this. Also, you'll see this. It's the same law. It's just rearranged a little bit, where the m is brought to one side or another. So you might see this sometimes, but I always like to introduce it with just the a first, equivalent to the acceleration. Okay. So that's the basic idea of Newton's law. So there are a couple more small things we're going to get into. So this is going to be the next section. This is going to be 3B. So in 3B, there's not too much to it, but it's all important. So when we're looking at objects, what we're going to do a lot of times is sketch a free body diagram, or FBD. And it's just basically a picture. It shows all the forces acting on that object. For example, this object right here, labeled with the mass, has one force over here acting on it, and then another force over here. And they're represented by these little force vectors. So we've seen force vectors before, or vectors before. Now we're going to be using them to make sure that we get the directions of forces right. So there's a lot of different types of forces. We're going to focus on just a few for right now. They're going to be the frictional force. So it's a force between objects in contact with each other that opposes that motion. So for example, if you have like a box and you drag it along a floor is nothing's ever perfectly smooth. So what's going to happen is you're actually, as you drag it across the floor, there's going to be a frictional force. So that friction is actually going to slow it down. So if you pulled it one way, friction is actually going to want to make it slow down. Again, if you drag anything over a surface, basically, you're going to get that force of friction. The next force is air resistance. It's a force acting on objects moving through air. So, like a baseball moves through the air, you're going to have the air actually pushing on you, slowing you down a little bit. And so you have a force of air resistance on you. And the symbol for force air resistance is going to be F, uppercase F with the little air underneath it in the subscript. And the force of friction is going to be capital F with a tiny f for the force of friction. And then the applied force is going to be next. So the applied force, it's Fa, just F with a little subscript A. It's just a general term used to describe lots of different forces on an object. Let's say you have an object and you push, a human's pushing it, or let's say you strap a rocket to it and the rocket is pushing it. Anything like that. It's used to describe just any force that doesn't, have a specific name. So it's just a general word for any undefined kind of push or pull. So those are all the main forces we're going to look at, and that's the idea of a free body diagram. So far we've talked about forces, different types of forces, drawing them in a nice picture, a free body diagram, just like this. This would be a nice free body diagram. And we've also, just to call back to the previous, so the previous one, we talked about Newton's second law. So in the last part, I know it's a lot of things. I'm going to show you an example for the last section, just so you see where this all kind of comes to play. There we go. So this would be an example of a problem you get. I want to show you what that would look like done out, and it's really going to tie all that stuff together. So what do we have here? We have a car traveling west. Okay. There's an engine providing a force of 10,000 newtons. So that 10,000 newtons must be west if we're traveling west. And the road's providing a force of friction. So we have friction in there too. Force from a surface, and it's 1,000 newtons. So it's asking what is the acceleration of the car if we know what its mass is. So again, ultimately we're looking, our unknown is acceleration. So how are we going to find that? We're going to start by actually drawing a free body diagram. So free body diagram would look like this. This is the car. This car weighs 2,000 kilograms. It says that it's traveling west, so we have the engine of the car traveling west. We're just going to write that as FA. And west would be a negative direction, so that's why I'm drawing it negative direction to the left. And then we have the force of friction slowing it down. So the car is actually moving this way to the left, how we drew it, and then you're going to have the force applied from the engine, and then the force of friction is actually going to be this way, slowing it down. And we're ultimately looking for the acceleration. So a good way to think about this would be Newton's second law, because that relates forces and acceleration. Write out the second law like this. Again, it was introduced in the notes like this, but sometimes this makes sense to move the move it around a little bit so we get the net force by itself. Again, these are both equivalent. So we're going to start to plug into this equation. We have two forces. We have a negative force from the engine, so negative Fa because it's going west. And then we have a positive force of friction because the force of friction is causing it, would want to cause it to move more east, or to at least slow it down from going west. So it's going to be positive because the force of friction is really in a positive direction. M, A. And now we actually know most of this. And we could solve for A because we know the mass that's given. Right, we have our mass right here. We have the force applied from the engine, that's given, and we have the force of friction, that's given. So really we just need to plug everything in and solve for A right here. So I'm going to plug in, we need to preserve the negative, but it would be 10,000 newtons, N, plus the force of friction, that's 1,000 newtons, is equal to, we got 2,000 kilograms, that's the mass, times A. And then what's going to happen is we just have to, we're going to combine these, so we get 9,000, negative 9,000, equal to 2,000 A kilograms times A. So your acceleration is going to be negative 4.5 meters per second squared, the standard units for acceleration. And this is a negative, in this case means west. I mean, it seems to make sense. If we're moving west, that means we must be accelerating west. So we're going to get, the best answer would be 4.5 meters per second squared west. Okay, so I would make sure you've taken a crack at this. You have this example written down. Your notes are notated. I actually went a little bit over my time limit. But that is the first section. So that is 2A and 2B, the notes, or 3A, 3B, the notes, and also kind of a nice example problem of what you're going to be seeing in the future. Okay, that's it for now.